Hello everyone and welcome to episode 4 of my Java bot tutorial. Last time we implemented a state machine and we have two states now. We have a boost collection state and an add state. Both of them derive from this move to point state that simply just tells the car to move to a point. And the add state will switch to the boost collection state when we have 10 or less boost. And similarly, boost collection state will switch to the add state if we have 60 or more boosts. And as we saw last time, this works, but it also means that our bot chooses to go for boost during the kickoffs, and that's not very convenient. So in this episode we'll make a kickoff state to make sure that the bot actually completes the kickoff, and then afterwards maybe it can go for boost. We are also going to look at something called local coordinates, which is something a lot of people use because it's just very practical. It will help us steer and navigate on the walls. And once we have that, it'll be a bit easier to get down from the walls. So let's make the kickoff state. That's simply just another state. And once again, we're going to extend the move to point state because in a kickoff you're really just moving towards the center of the field. We can come back later and make this more advanced and maybe add a dodge or a special pathing, but for now we're just making sure that we actually get to the ball in time, and we want to boost all the way. So for our kickoff, our target will be the center of the field, which is 0, 0. We could also choose the ball as the target, but the ball is at the center anyway. Our target speed will be as fast as possible. And now once the kickoff is over, we want to switch back to one of the other states. So the way we detect kickoff is actually a bit tricky. There's a value in the GameTech packet called isKickoffPause. And this is a boolean that is true while the clock, like the game timer, is paused due to a kickoff. This is actually not true during the countdown. It is true from the moment the car can move and until either the ball has been moved or some amount of time has passed, in which case the game timer will also start ticking down again. So generally a good way to detect the kickoff is to test both the timer and the position of the ball. First, let's just check if our kickoff pause value is in our data packet. I don't think it is. Let's add those game values here. So in this game info, you can find different things like the game speed, how much time is remaining, whether the match has ended or not, overtime, is round active, and that's just general. Are we playing right now, or is there a replay, or is it paused or something? We can also see if it's unlimited time. We can even see the gravity, because that one can be changed in Albert. But yeah, we are interested in this isKickoffPause. And we also check the ball position, and we flatten it first so we can just compare it to the 0. There might actually be an is0, yeah. And now that we are here, let's just add some values for the timers, because those are going to be important later. So we also have time and time remaining whenever we need it. Let's go back to the kickoff state. And here we simply check whether it's still a kickoff. If it's not, we're going to change to the admin state. Great, now we just need to make sure that we actually enter the kickoff state. And we want to enter the kickoff state whenever a new kickoff begins. And this has to take priority no matter which state we're currently in. And to do that, we'll actually place it in the goblin itself before we check our current state. So here, instead of just executing our current state, we'll just make sure whether or not we are in a kickoff. So you can think of this as we have actually wrapped a state machine around our state machine, one that always takes priority, like this. And once the kickoff is done, we'll go back to our regular state machine. Let's try it out. Our bot is now running, great, no compile errors. And let's run Albert. Now let's see how he does in the kickoff. That looked pretty good. He didn't go for boost, and he actually scored on the kickoff. And he actually isn't boosting all the way because he doesn't have boost enough, but he still gets there before the rookie. And that's a thing you'll find in the Albert community. Kickoffs are very important. If you don't have just a decent kickoff, so many bots will beat you and they will just destroy you just in the kickoff phase. With something simple like this, your end chances are already way better. And once we have a dodge, it'll be even better. And yes, he is still switching between the other two states. When he runs out of boost, he will go for boost, and once he got some boost again, he will go for the ball. He does, however, still drive on the wall, and that's the next thing we'll fix. Now before we move on, there's just one inconsistency that I want to fix. I noticed that our data packet and our game tick packet are called different things. So I want our data packet to always be called data. So let's fix it here. And in the data packet, the game tick packet was called request. I want that to just be packet. There we go. Consistency is nice. And now we can move on and talk about local coordinates. It's going to be relevant for our move to point state. So what is local coordinates? Well, with local coordinates, we're trying to see the world from our bot's perspective. Like from the car's perspective, how far is the ball in front of me, how far is the ball above me, things like that. And to do that, we have to consider the difference between our car and whatever we're looking at, but we also have to consider the orientation of the car. To calculate a local coordinate, we do something like this. Okay, so the idea here is that we make a new vector, and each coordinate is our car to target vector dotted with our forward, left and up vector. So the result is that the x component would tell us how far in front of us is this target. The y component will be how far to the left, and the z component will be how far above it. And this pattern here is something you'll see a lot in Alberts. We find the difference between us and the target, and then we calculate what is that difference from our car's perspective. I hope you can kind of imagine what I mean with perspective. For example, if we are on the wall, then our car is sideways, and everything will be kind of above our car from our car's perspective. And it's important that we can tell this difference, that our car is rotated, and we have to take that into consideration. So how are we going to use this local target? Well, first let's go down and replace this car to target with our new local target. So now our bot will be able to tell whether the ball is to the left or the right, even if we are on the wall. We are not going to change this one because we are going to get the same result. We just want to know how much of our velocity is in this target direction. And that's going to be the same no matter if we are using local coordinates or not. Now the next thing we want to do is to make our car go down from the wall. So first we are going to need a way to tell whether we are on the wall or not. And this would be a great value to add to our car data, so the value is always ready for us. Let's add this value here. It's just going to be a boolean. And the way we're going to calculate it is by comparing our up vector, like the direction from our car and then through the roof, and we're going to compare this with the up vector of the world. And if those two differ too much, then we know for sure that our car is not on the ground. So here we'll compare it using the dot product again. So if the two up vectors have the same value, the dot product will be 1, since both of these vectors have a magnitude of 1. And if it's lower than that, we know that they differ. If it becomes 0, our car is actually sideways. So we will use some kind of in-between value like 0.5. And if it's less than that, then our car is at least not upright. So actually we could also be on the ceiling or something. Maybe it's actually better to call this value for is upright. And let's add a comment to that so we can remember it. So this will be true when our car is oriented upright with the wheels towards the ground. And it's false if our car is angled in any way more than just a little bit. So it can also be sideways or upside down. Okay, great. Another thing we're going to use is this has wheel contact. And these two combined, we can check whether or not we are on the wall or on the ceiling. So let's go back here and use those two. So the way we are going to do this is we are going to check whether we are on the wall, and if we are on the wall, we won't actually go towards the specified target. We'll go towards a target that's a bit closer to the ground. And that way it will force our car to go down from the wall, but still in sort of the same direction as it's supposed to. Like the direction we actually expect it to go when we order it to go towards this point. So we're going to shadow the target variable up here and make a new target that is the same target, but the set value is now only half the amount. And we're only doing this if we're on the wall. So our wheels have contact, but we are not upright. Well, in that case, we want to go a bit down instead. And actually this value has to be introduced here in the outer scope. There we go. Let's just add a comment here before we forget. Now let's test it. Rerun the bot and let's go back into Rocket League. He seems a bit confused. Maybe we did something wrong. Okay, I found the bug. That's my mistake. Of course, the local target here, we can't dot it with our orientation, because our orientation is in world space, and this one is in local space. What it means is that we basically have to make this into a vector that points straight to the left relative to a car. So that would be a new vector 0, 1, no wait, 1, 0, 0. But this is the same as just taking the x component, so we could just say local target normalized .x. No wait, not x, y, because y is our left coordinate now. Let's try this. And yes, it's now steering correctly again. Okay, so after watching a bot for a bit, I still don't think it's doing very well on the walls. Okay, so it turns out there's actually a bug, and it's in our car data. Oh, car data, yeah, there it is. I put the wrong sign here, it should have been greater than. Because as I said, if it's 1, then we are upright. If it's below 0.5, then we are probably not upright. But there's another thing as well. Here it says flatten, and that's not what we want. Now we want to be able to have the set component as well. That's why it didn't work on the walls. We completely ignored that dimension. But during my testing I also found a different kind of target that were way more effective as just getting down. We take the car's position and we flatten it, so now we have the point that is right under our car. That will obviously make us go towards the ground, but to avoid a divide by 0 error we also have to just move it a bit, and we'll just move it towards the center by scaling it by something like 0.9. And now our car is way better at getting down from the wall. Just see here. Works great. Actually, let's render the point we're going towards. I'll show you how to do some rendering. So with debug rendering we can draw lines in the game. You've seen it already. And to do it we need to get a renderer for our bud. This is done like so. Bud loop renderer for bud loop, and then give it our bud. Now we have a renderer and we can simply call renderer.drawLine3D. Let's make it a red line. We want to draw from our car's position to our target, and that should be it. Rerun again and let's see in game. And you can see there's always a red line towards the current ball when we are adbang. Now it's going for the boost. And when it's up the wall you can see that it will change the red line here, and it's actually going towards the ground. Now of course this is still just super simple behavior. We don't really consider much except that we are on the wall, we want to get down. Okay, so there's one more thing we want to fix in this episode, and that is that our bot will boost even if it's boosting in the wrong direction. So here it was boosting sideways, and if we overshoot the ball we will also start boosting again. There you go. And that's not what we want. That's just a waste of boost. So we only want to boost when we are facing our ball or facing the target, whatever it might be. So here when we are deciding whether or not to boost, we need to consider, are we facing the correct direction as well? We will be facing the correct direction if our orientation vectors forward is in the same direction as our car to target. And to do that we once again use the dot product. So here we will add okay, so this new condition simply compares a forward direction with a car to target normalized, and if the dot product of those is greater than 0.8 then they are approximately in the same direction, so that means we can boost. And yes, this works great as well. As you can see here, we only boost when we're actually facing the ball or whatever we're going towards. Oh no, we're overshooting the boost pad. So this seems to be working great. Our butt is now way more boost efficient. And that's it for this episode. See you in the next one.